Good afternoon, everyone. Can everyone hear me?
Yes, Pranay.
No. Good afternoon, everyone. I am GN Parindra of Cre'active team. I'm a
Good afternoon,
volunteer.
everyone. Can everyone hear me?
Yeah, you are audible.
So Cre'active, let me give a little introduction about Cre'active. Cre'active is a team of curious minds who crave for knowledge and exposure, which includes students, engineers, teachers, and individuals from almost everywhere. We cater in creating awareness about scientific temper and various other domains in people. It all started with an idea of a teacher at a college, and we are all so proud of where we are right now, as we even got recognized as ISRO space tutors. Now, about today, the talk is about the Mathematics Day. So now I'd like to ask Varsha, who is studying ninth grade at Dr. Ambedkar Residential School, Gauri Vidnuru, to give us insights on the importance of Mathematics Day. Over to us. Sorry, everyone, there might have been a little issue, so we're facing a little technical issue. We'll get back in a minute.
Good afternoon and everyone. I am Varsha Reddy PS from class 9th standard from Dr. Ambedkar Residential School, Gauri Bidnar. On this National Mathematics Day, as we honor the brilliance of Srinivasa Ramanujan, let's look into a few glimpses of his extraordinary life. Ramanujan, born on December 22nd, 1887, in Erode, India, displayed an early aptitude for mathematics. His journey into the world of numbers took an unusual turn when, as a young clerk, he independently discovered complex the theorems and formulas without any formal training. His notebooks filled with groundbreaking mathematical insights would later become the cornerstone of his legacy. Despite facing financial hardships and health challenges, Ramanujan's passion for mathematics remained unwavering. His talent caught the attention of British mathematics GHRD, leading to collaboration that would significantly impact the mathematical community. Their partnership resulted in groundbreaking work on number theory, infinite series, and continued fractions. However, Ramanujan's life was tragically short lived. He did not live for more than 32 years. His contributions to mathematics have endured the test of time, influencing generation of mathematicians. As we celebrate National Mathematics Day, let's not only appreciate Ramanujan's profound intellect but also draw inspiration for his resilience, unyielding passion, and the remarkable journey of a self-taught genius who transformed the landscape of mathematics. Thank you, Cre'active, for giving this opportunity.
Thank you, Varsha, for your introduction or insights about Mathematics Day. Now, let us get to know our speaker. Dr. P.B. Mishra possesses an extensive scientific background, serving as the head of Flight Dynamics Group at the Indian Space Research Organization (ISRO) ISTRAC in Bengaluru. With 16 years of experience as a scientist at ISRO, the professional has played a pivotal role as a project manager for flight dynamics operations in the Gaganyaan mission, demonstrating leadership in critical space exploration initiatives. The academic journey includes earning a PhD in Finsler geometry from DDU University, Gorakhpur, India in 2007, showcasing a strong foundation in mathematical sciences. His research interests evolve around celestial and orbital mechanics, particularly focused on spacecraft orbit determination and the prediction utilization, very long baseline interferometry techniques. His commitment to advancing knowledge is underscored by the publication of 26 papers in renowned international and national scientific journals, with the notable recognition through 3 Best Paper Awards at different international conferences. Furthermore, participation in the International Space University Space Study Program in 2019 and serving as the member secretary of the International Conference on Spacecraft Operation and Space Situational Awareness further and highlights his dedication to the field. His achievements extend beyond the realm of research and academia, with 4 gold medals earned during post graduation and a notable Best Paper Award received at the International Conference on the Space Situational Awareness. Additionally, qualifications include success in the Council of Scientific and Industrial Research (CSIR) as a junior and senior research fellowship in mathematical science in June 2003, showcasing a well-rounded and accomplished career in space science and mathematical research. Now over to you, sir.
Whether I'm audible?
Yes, sir, you are audible.
Good afternoon,
Good afternoon,
and
sir.
thank you to very energetic, creative, and creative group. I believe this is,
Yes, sir. Yes.
and I am very thankful to Dr. Supriya, my friend Srinath, and the creative group who has provided the opportunity to deliver a talk on the topic of mathematical sciences in the space field. On the occasion of birth anniversary of great mathematician Srinivasa Ramanujan. So already we heard a very good narrative about Ramanujan with the student. Now, further wasting much time, I will start my talk. So, shall I go ahead?
Yes, sir. You can go ahead.
Whether the presentation is visible to all?
Yes, sir. It's visible.
So, as I mentioned, this talk is on the occasion for the birth anniversary. Whether slide is changing?
Sir, no, sir. Only first slide is visible. Mathematics, science, and research is visible.
Next
Now,
slide.
yes, sir. Now it's next slide.
Yeah. So you can see the photograph. Of course, I have taken from the Google. So the courtesy is from Google only. But here you can see I'm just starting my talk with my tribute to great mathematician Srinivasa Ramanujan. I believe this is the paper written by him, some of the mathematical identities, where you can see that he has tried to derive the sum of cube of two integer can be written as another sum of the cube of another integer with the identity of -1. So this is the one of the thing which I am showing, but he has almost solved more than 4,000 problem which was not solvable at that point of time in his very short period of life. And major things has been already told, so I will not repeat all those things. But my tribute to Mr. Srinivasa Ramanujan is, if you see his date of birth with time, which is 22nd December 1887, and what I understand that the timing was 6 p.m. And since he was genius in creating the matching with numbers, so I also put a small effort to use these numbers. And what I did, if you check, I've just added the year with this month minus date into same month minus date plus the time of birth. And then I multiplied the month and date. What we are getting is a 1729. You can cross verify, but this all thing, this 1729, you can see can be derived by his date of birth and time, which is a very, very well-known number. We all know this 1729 is a smallest positive integer which can be expressed as per this identity as the sum of cube of two integer in two different ways. That is the smallest number, and we call this Ramanujan Hardy number. So this is my tribute to him. So further not wasting much time, I will go to the actual talk. That is the application of mathematics in space. So before going the application of mathematics, I will just try to give some of the glimpses like what kind of study we do in the space research. Basically, by launching the satellite in the space, we try to study two parts. One is the terrestrial study, and another is the planetary exploration. The terrestrial study, for doing terrestrial study, that means we are going to study about Earth, on the Earth, and between the Earth and the satellite, what is happening. So based on this study, we create different kind of application and we launch different kind of satellites. We generally do the remote sensing, navigation, communication, weather monitoring, even strategical satellites, and many more. So you can see in the pictures those different kind of satellite like remote sensing, navigation, communication, even space stations. These are all satellites are being planned based on the application, and they have been put at a particular altitude over Earth, and they are rotating around Earth. Now coming to the planetary exploration, there we study the celestial bodies, our planets, neighboring planets, even outside of solar system, and also human presence in the space. So this is what we study in the space research. Now coming to the some of the things where maths is directly involved, or I can say without math means you cannot further move, which start from the rocket itself. As we all know, to launch a satellite from where we all get all the results and applications or data is being injected through rocket. So the problem start from beginning itself. Like if you want to inject a satellite of suppose 2 ton, at least you need to build with existing technology in India rocket of nearly 300 ton of PSLV rocket, which can carry a satellite of 2 ton and can put a satellite at 600 kilometer circular orbit. So this is how it is very, very costly. We are injecting a satellite of 2 ton, but for launching that satellite, we need to build a rocket who can cross the Earth atmosphere against the gravity, and also considering wind, it will be trying to inject. So all this calculation, like how much thrust is required, what should be the flight duration, what should be the trajectory, what should be the attitude of the rocket so that it can inject the satellite at designated place. These are all things are being mathematically computed and estimated before the launch. And they are going with the rigorous mathematical modeling and so many other algorithms. So the work means the rocket launch vehicle trajectory design to its weight, structure, everything are mathematically computed at the design level and being implemented so that we are able to launch the satellite at the designated injection point. So work start from here. Then further going down, like every spacecraft it design, as I mentioned, based on its application, it can be the for the remote sensing, or it can be for the navigation like GPS or Indian Navy constellation or Galileo or GLONASS, or maybe communication or many other application. We design the spacecraft orbit. When I say orbit, means we try to design at what altitude we supposed to keep the satellite so that our application will be met throughout its orbital operational period. And based on that, we also estimate what's supposed to be the lift-off time for the launch vehicle to inject at that particular geometry. So here comes to the geometry as well as the orbit design, and lot of differential equation you need to solve, and uh, you will be computing how my spacecraft orbit design is going to be taken place. Now, further down the line, if you are making some satellite which is going to be in interplanetary mission like Mars, Chandrayaan, or even away from the solar system, then the very challenging task comes is the interplanetary trajectory design. And nowadays you might have seen recently, means we landed on the moon, and in the future if you are planning to land, roam around the moon surface and come back to earth again safely, you need to work out all this trajectory, that how to design the orbit, then how to land safely, and again how to come back. So these are all challenging problem of mathematics. Of course, the time what is we have here, we will not able to cover most of the things, but I will try to cover some part of the interplanetary design, trajectory design at basic level, so that you will get the motivation and try to understand. These are not very challenging, but once if you put the interest, then you will feel the real scenario, and then you will be trying to bring some new things which will be really helpful for the world itself. And also there is another challenging and the important problem is to generate the future position and the velocity of the spacecraft, where it is going to be at what time, so that you can plan your operation well in advance. And it also required for the safety of the spacecraft. As we know, through around the earth we may have more than 40,000 debris, so you need to keep the eye on each object which are rotating around the earth in the orbit, so that you can make safe your own operational satellite with any further accident or collision. Similarly, the another challenging problem, it's not the challenging problem, but it is huge level of mathematics used for your spacecraft navigation. Like we, on daily basis, we are using the GPS, everything in our life, and city life is much flooded with that. But just if you go back and see how these things are being derived, that at any point of time, instantaneously, we are able to tell where we are and what is our plan, and what is the trajectory to go to another destination. So these are all things are being calculated instantaneously in real time using good mathematical algorithms, using estimation techniques and numerical integration. So these are the some of the application where in a space field we use a lot of mathematics, and I'm again reiteratively telling there are lot of scope to improve to have more precision in our results. Whether I just wanted to know in between any whether any question answer also will be there, or I can go ahead with my presentation.
So in the end, there will be a Q&A session. Like after the talk, in the end,
Yeah.
if they have questions, they'll ask in the end.
Right. So, okay, thank you.
Okay.
So, what I was trying to tell in the last slide, like some of the applications of mathematics, without that you cannot think about the any space research or spacecraft launching or rocket launching. But here I will just give one of the example where we will try to learn or try to understand like how the interplanetary trajectory design is being made at the mission design level itself. But before going to that, I will just try to tell why deep space mission we are looking for. What are the application we are getting through the interplanetary mission like Chandrayaan, Mangalyaan, and Aditya L1 mission which is going on, and future many mission from many other agency like NASA, JAXA. But of course, so since many students I believe they have joined, I'm just trying to say here that for the deep space mission, basically the what we are looking, that we are trying to explore the planet atmosphere, like we have the atmosphere around earth, whether there is such other planets where some atmosphere exists. Because for our human life we need to have such kind of things like land, water, and atmosphere. These three things are essential as if now. So we try to explore whether such atmosphere exists. For example, if you see there is thin layer exists over Mars, but there is no atmosphere around Moon. So similarly, any other planets inside our solar system or outside of solar system, such kind of things we are just trying to explore using the spacecrafts which are being launched. And so that if some opportunity comes, then we can think about the inhabitation or colonization on the other planets. And also, like presently, if you see ISRO launch Aditya L1, which is very close to its I means orbiting around the Lagrangian point. Maybe on 6th January it is going to be. So such satellites are very helpful to predict and provide the alarm to our planet Earth in terms of providing the sun storms or any other corona mass ejection, such kind of data we will be getting, and will be well prepared for our safety. And some of the satellites also can be used as a gateway for the interplanetary travel. Like we can use the satellite around the moon, and from there we can add some gravity from the moon, and without wasting the fuel we can approach to some other planet. So this is our some of the application which are being used, means which are being used for the deep space mission. Apart from this, some of the other applications also are being utilized using interplanetary trajectories or interplanetary missions. For example, if you are seeing like if you are developing electronics or a subsystem which are well qualified for the space, even beyond the atmosphere, and then such kind of things are can be used in our daily life and used as a spin-off also. So these are the applications which right now, or even many more are there. We can get it from the deep space missions. So, but there are many challenges for having a deep space missions. Like as I told, you will be facing so much radiation, extreme temperature variation from minus to plus, and another challenge is like the communication. Suppose if you are planning a satellite over Mars, so you can think of the distance itself, maximum maybe 22 crore kilometer more than the sun from Earth to Mars at some point of time. So, and the signal travel with the speed of light, like something like 3 lakhs kilometer per second. So the turnaround time one way itself is 20 kilometer. So you can think of that whatever signal you are sending to the satellite to do a certain job, it will take all the way 20 minutes, and coming back also 20 minutes. So the response itself you will be knowing maybe after 40 minutes. So it's a huge time. So we need to build the satellite in such a way that the all onboard autonomy should be onboard itself. Autonomy should be built onboard in itself, so it should be able to take its own decisions. So this is one of the challenge, what and major challenge what any deep space mission will be facing. And secondly, since the signals are coming from very long distance, you need to have a very deep space station at the ground, which we like ISRO is having 2 DSN, 3 DSN station at the Vayalalu near Bangalore to acquire the data and also to send the command. And similar and again the major challenge to have the manage with the propulsion system, because you have to go to away from the earth where you may have to go, means you have to definitely go more than the escape velocity of the earth. So you need to provide more energy to the spacecraft, which is again a function of fine cost and such kind of engines. And again, suppose if you are planning the mission for the Mangalyaan or even beyond solar system and all, in between you have to switch off the engine. Again, when you are reaching to the planets, you have to switch on or turn on the engine. So these are the challenges in for this long period of time of 1 year, 2 years. How the system will be have, this kind of test has to happen before going to the mission. And I was telling the most complicated and challenging task is the designing the trajectory. For example, if you are going to land on the Mars, then you have to plan the trajectory in such a way that you should not take more time, should not use more fuel, and even you should not hit the target or you should not fly by. So these are very tough problems of having the interplanetary mission, but these are all being solved with a very mathematical modeling, which I will come later. And then again, other challenges like you need to know at every point of time that where the satellite is, because these satellites, when they are going in the deep space mission, will not be having the GPS or Navic where it will compute its low position. But you need to have your own navigation system using new means new and wider technology like very long baseline interferometry, where we use the delta dr techniques. So these are the challenges what we will be facing to design a deep space mission. Now I'm just giving one slide what ISRO has done so far in terms of the deep space mission. So far we have 5 deep space mission. The first launch was Chandrayaan-1 in 2008, and the objective of the mission was to orbiting around moon, and it does the job 100% and created the history by finding the signature of water on moon, and that is also near South Pole. And the second mission was Mangalyaan, which was launched in 2013, and it has captured the Mars almost after 1 year in 2014, and that also created a history in the field of space because it captured the Mars in its maiden attempt. And subsequently, the life of Mangalyaan was designed only for 6 months due to the eclipse constraint, but it survived more than 7 years. Now coming to Chandrayaan-2, in my view, it was a very successful mission and gave a very big boost for the success of Chandrayaan-3. And it also has created a history now by, I can say, because we have a camera on the Chandrayaan-2, which is the best resolution camera what we have. And initially the life of Chandrayaan-2 was also very short, but still it is working almost after 4 years and be giving very good result. And I need not to talk much about the Chandrayaan-3 because it's known for world and it has already created history by landing softly and safely on the South Pole. And another deep space mission is Aditya L1 of ISRO, which is on the way on its journey. And by 6th, it will be capturing the Lagrangian point. You can see this is the Lagrangian point, which is a factitious point. You cannot think about a orbiting around a point until unless it doesn't have the gravity. But you see the beauty of physics and maths that between Sun and Earth, there are 5 points where the centrifugal forces of the masses will be equalized. So there are such 5 points can be exist, and with this point itself has found by solving their differential equation. So this is one of the point L1 point which we call as Lagrangian L1 point, and the plan of Aditya L1 is to orbit around this point. Now coming to the some of the basic part of designing the trajectory are some of the application of mathematics. As we all know, as per the Newton gravitational law, that the force between two objects, where the one object is rotating around the another object, and if the distance between these two is r, so as per Newton gravity law, the force, which is the acceleration acting on the body, will be proportional to their mass product and inversely proportional to the square of the distance. So if you say the acceleration is r double dot, and if you take the cross product with r, then definitely we know the r cross r double dot will be 0. So we can say the vector which is perpendicular to the acceleration and the radius vector is 0. So what we can say, there is no external forces acting on the spacecraft perpendicular to the orbital plane. That means once we launch the satellite around the Earth or any other planet, there will be no external forces which will be disturbing the orbital plane. So, and if you integrate this equation once again, you will get r cross r dot is equal to h, which we here, that is nothing but the cross product of position and velocity, which is nothing but the specific angular momentum, and it is going to be constant. So in other way, we can say the motion of spacecraft around Earth possesses the specific law of angular momentum, conservation of angular momentum. And this is exactly the Kepler's second law, which we are deriving from the Newton law of gravity. So you can see the beauty of mathematics, that you need not to know the Kepler law, but if you know the Newton law, then you can derive using small mathematics that it follow the Kepler's second law. And again, if you further simplify this equation, r cross r dot is equal to h, by taking the cross product, you will be getting an equation like L by R is equal to 1 plus E cos theta, which is, we know this is a polar equation of a conic section. So as per the Kepler first law, he has mentioned that planet will be rotating around the sun in a conic section, in a elliptical orbit. So again, you are going to prove the Kepler second law. Further, if you modify these equations, you will be getting the time period of the closed orbit will be proportional to the cube root of the semi-major axis, average semi-major axis. So what I'm trying to tell with this is small elementary mathematics, that by just applying a physics of Newton law of gravity, you can deduce all Kepler first, second, and third law. So this inversely you are trying to prove this. But I will just try to focus on this equation where you can see the velocity v square is equal to mu 2 by r minus 1 upon a, where v square I can say is a specific kinetic energy and mu by r is nothing but the potential energy, and a is the semi-major axis which is fixed for the orbit of the satellite. So you can say the motion of spacecraft also possesses the law of energy, conservation of energy, and that means kinetic energy and potential energy is going to be same. So now using same equation, one can design the orbit for even low Earth orbit satellite based on the application, or navigation satellite, and then you can find out how much velocity will be required for the given altitude. Like for example, all the remote sensing satellites, IRS satellites, or even future upcoming Gaganyaan missions, they are being planned below the 1,000 kilometer height, and the reason is very known reason that they need not to face the more radiation and other effect which are above the our Earth atmosphere. So, and their major job is to take the picture. So lower the height, better the picture. That's why they are planned in the low Earth orbit. So if you are planning a satellite at 400 kilometer, so the required orbital velocity should be 7.67 kilometer per second. 7.6 kilometer per second. You can think of how what should be the velocity of the satellite at that height, and of course our Gaganyaan mission is going to be at that orbit, and the orbital period will be nearly 92 minutes. Similarly, using same equation, v square is equal to mu 2 by r minus 1 upon a, you apply, you can get all this. And these are very small level of mathematics which we have used for designing the missions. So similarly, if you look for the navigation, where the all GPS satellites are there, they are nearly at 20,000 kilometer at height, and they're basically why these are planned I will come later. But if you see the required orbital velocity will be something like 3.9 kilometer per second, with the orbital period of almost half of the day, around 12 hours. And the communication satellites are being put at 36,000 kilometer height because of their application. They have to be designed in such a way that they should be able to have the contact with a part of the Earth's surface in continuous mode. So by keeping 36,000 kilometer height, you can see the orbital period is almost 24 hours. And we also know the Earth is rotating about its axis around 24 hours. So the contact between the Earth surface and the communication satellites will be always in intact. So these are satellites are being used for the communication and the broadcasting. Similarly, if you want to put, because moon itself is another satellite, what I can say, of the Earth, which is almost at 3,86,000, and the orbital velocity is 1 kilometer per second. So keeping these numbers, we are particularly designing the satellite, and accordingly the selection of the launch vehicle is happening, like based on the payload mass and based on the orbit of the satellite, the selection of the launch vehicle is being decided, and then its trajectories are being generated. Now coming in a small part, which is also linked with the interplanetary trajectories design. Let us consider a case where we wanted to go from Earth to Mars. Suppose this inner one inner one circle is a Earth orbit around Sun, and the outer one is the Mars orbit around the Sun. Of course, I have treated both are circular, but in reality, it is not. They have small eccentricity and they have little ellipticity, I can say. But for the starting and designing the mission, we can think of the Earth rotating around Sun in a circular orbit and Mars also rotating around Sun in a circular orbit. But our problem is to go from Earth to Mars. So suppose if you see in 2D in Earth fixed coordinate system, then you can join a ellipse, a intermediate ellipse between these two circle, and with this path you can go. So this is all can be done using Harman transfer, which is this is nothing but a simple generating a geodesic between two functional or the circular orbit to go from Earth to Mars. And these are the formula which are derived and being used to compute how much velocity I need to give at the beginning of the Earth, which we call the departure trajectory, and how much velocity we need to reduce after reaching to Mars to capture the Mars. So this is what the same technology are being used throughout the world to compute what should be my trajectory to go from one planet to another planet. Now, I have just taken an example of our Mangalyaan mission, suppose if you have. So how you can design and you can find out what kind of fuel will be required and when I can launch and what will be the opportunity. So just give little attention on this picture. This is again the picture what I shown in the previous slide in different way. Suppose this is Sun and this orbit is your Earth orbit around Sun, and the outermost is the orbit of Mars around Sun, and we have injected the satellite from Earth here, and we wanted to capture the moon at point A. So that is nothing but the point A where we wanted to capture, and point D is the departure time. So using Harman transfer, one can compute what should be the velocity required to go from Earth at Earth sphere of influence to come near to the sphere of influence of Mars. Here I am using a term called sphere of influence. So sphere of influence, I mean to say the meaning of SOI is that the altitude beyond which the impact of gravity of the planet will not be sensitive on the satellite. That means at what altitude the satellite is not going to rotate around Earth. In other words, it is going to cross the Earth centric motion to the sun centric motion. So this is the formula to compute the sphere of influence of any planet around sun. What is unknown here is the masses of the sun and the planet and the radius. So you can apply this formula, and this is again I just wanted to tell this formula itself is derived using lot of many second order non-linear differential equation, and using linearization through the Taylor series this formula is derived. So of course once you do the linearization, then some error still will be there, but this is sufficient enough to design the mission that if I want to go to Mars from Earth, I need to cross 9,25,000 kilometer distance. Otherwise, spacecraft is again going to rotate around Earth. It is not going to move towards the designated trajectory towards Mars. So we need to achieve this. So in that case, you need to provide the velocity which is supposed to be the more than the escape velocity of the satellite. So now, if you see, we know the Earth is rotating around Sun with almost 29.8 kilometer per second. And since we wanted to cross this altitude, so the required velocity with respect to Sun will be something like 32.7 kilometer. So what additionally velocity has to be produced from the spacecraft is 2.94 kilometer per second with respect to Sun, and with respect to Earth, it will be almost 11.4 kilometer per second. So this is the velocity required at point D to go in this path towards Mars. But suppose if you have a launcher like PSLV, which can only provide something like 9.9 kilometer per second at the injection because of its own structure and limitation for the given payload mass, then you need to fire almost 1.5 kilometer per second delta velocity you have to gain by the satellite engine. That is a extra weight on the satellite, which is if your rocket is directly able to give 11.4 kilometer per second delta velocity, it is well and good. But if you don't have such kind of technology, then you need to carry that much fuel along with the engine, which is a extra payload mass which you carry through the satellite, and it is a cost penalty. As I told, the launching a 2-ton satellite itself required something like 300 ton of rocket payload mass. So these are things based on the technology what we have existing. We carried with Mangalyaan, and during departures, we gained the 1.5 kilometer per second extra velocity we added in the spacecraft. Now, the other part what will come once you come near to the Mars, using same formula, one can find out what will be the sphere of influence of Mars. Like the satellite has to rotate around Mars, then it should be within the sphere of influence, and therefore we need to subtract the velocity over Mars. So using same formula, we know since uh, Mars is rotating around Sun with 21.4 kilometer, and with this velocity of 11.4 kilometer when you go, or I can say 32.7, then you need to reduce the velocity of something like 0.8 kilometer per second by reversing the engine. And this is how you can design the trajectory, and the travel time from this point D to point A, which we call the cruise phase or the transfer trajectory, will be almost 258 days. And another calculation what we need to do before planning these missions, the opportunity, because we need to ensure the minimum fuel only should be used during the departure or arrival. So this criteria is being derived based on the phase angle between Earth, Mars, and Sun at the departure and also at the arrival. So once you put this constraint, so this kind of opportunity comes almost every 796 days. So once if you have a mission now, then the next opportunity for Mars will come only after 796 days. And then suppose if you are planning in the future to go to Mars and come back, then again you need to wait for the same phase angle, which will come after 453 days. So if at all, with the current technology, with the minimum energy transfer, if you are planning to go to Mars, then almost 3 years, one journey will be there, going, waiting, and coming back. And the next plan will be only after 796 days. So you can understand, even though Mars is having thin atmosphere, land, and maybe some kind of structure which can help to get some kind of water, but still with the current technology, this is how challenging is. And this is the best what we have now. So, but of course, there are a lot of research are going on to reduce the travel time to the interplanetary mission, and if people also can focus with your mathematical knowledge that how this trajectory can be further optimized. This is how one can plan Mars mission trajectory. This is one of the video I just wanted to show, but I think we are running out of time, so I will skip this. Shall I skip this?
Sure, sir. If you want to skip, you can.
No, PD,
Okay.
if you can play, it will be good. Please play, because this is thing
Okay.
which students will
Yeah.
not get opportunity to see.
Okay, right. Thank you, Srinath. So this is one of the, I can say, is a real picture where in the down you can see this is running with the time. So this is the actual trajectory of our Mangalyaan mission. Here you can see the blue orbit is the Earth orbit around Sun, and you can see currently Earth and the satellite and as well as the Mars all are moving around Sun. So whatever I explained to you through the two circular orbit and one transfer trajectory, you can visualize here. And if you see Right now, this white color is the trajectory where the Mangalyaan is approaching towards Mars. And after 258 days, you will be seeing it is going very near to the Mars. And once it comes very close to it, then it will be capturing the Mars. So this is how we design the trajectory and we capture the Mars with our Mangalyaan satellite, which operated almost seven years of its operational life. So I am coming to the next, which is again another kind of interplanetary trajectory, and I'm just talking about the Chandrayaan 3, which has already created history. But here, just I wanted to tell whatever I told you, the trajectory design are going to be same for the Chandrayaan 3 also. That we need to generate a transfer trajectory between Earth and Moon, but we have to have only one cushion here, that Moon itself is rotating around Earth. So your departure trajectory, which was the hyperbola with respect to Earth or Mangalyaan, is not a hyperbola. Here it is going to be ellipse, because if you miss the opportunity also, it is going to rotate around Earth, because you are only capturing Moon, which is again rotating around Earth. So that is only the difference between the Mangalyaan and Chandrayaan mission. Otherwise, the trajectory designs are going to be same. So, but just I wanted to focus here, and little bit I wanted to tell on the Chandrayaan 3. We not only achieved our important goal of landing softly and safely on Moon, but due to the meticulous planning and operation, we were also able to do some two new experiment, which was really required in the future mission, where because we were having some fail in the lander module after landing, and with that we tried an successful experiment of doing the hopping, that means lift off from the moon surface. Our lander was taken up and again safe landed, so you can say it is landed 2 times safely. So that was also done. And again, the propulsion module, which was another, I can say, mother or sister, you can say, for the lander module, because the lander module was separated from the propulsion module, was still orbiting around moon in 100 by 100 kilometer orbit. But since some fuel was left out, and we used our trajectory design in such a way that it added some velocity from the moon, and now currently it is orbiting around Earth. So in one mission you have achieved three type of objective, I can say, which was bonus from the mission: that you have landed safely, you have lifted from the moon surface, and again you are rightly rotating around Earth, means you are trying to bring back from the sphere of influence from the moon to Earth. I think time is very less. I will try to conclude my talk with some of the photos here. These are the photos which you may be seeing in the public domain also. You can see the lander, how it is softly landed. But for us, it's a very beautiful picture and a historical picture. So just I put some picture here. And here also I have some video of the Chandrayaan 3. I will try to play little faster. So you can see here the propulsion module, which is now separated, and this is the lander module, which are going to land softly and safely on the designated landing site at the South Pole. So this is the courtesy goes to the ISRO headquarters. From there I got this video, and you can see the separation here. Then I'm just running a little fast. So as I mentioned, for any deep space mission, you need to have the deep space network throughout the globe. And we also got the support from not only a IDSN station, but also from NASA and the European Space Agency. And this was the trajectory what was designed for the power descent. And now you can see the lander, after separation from the propulsion module, was rotating in 100 by 30 kilometer orbit. And after with this 30 kilometer, it was power descent was started, and there were 4 phases. During the rough braking phase, it was coming from 30 kilometer to 7.4 kilometer altitude, where it has traveled almost 713 kilometer in the slant range. And after reaching here, it does the one kind of hovering for testing its other sensor of altimeter and to get the actual information of current altitude from the moon surface. And once that experiment was done, it again went in the attitude hold phase where the attitude of the lander module was fixed, and it successfully did all the experiment and calibrated all the sensor up to 6.8 kilometer. And subsequently, it has started from the attitude hold phase to fine braking phase, and yeah, it reached up to 800-meter height from the land, means the designated landing site. And the design was there. If any anomaly or anything is happening, it can just change its trajectory from 150 meter to get the designated point based on the hazard and other data which will be acquired from all these sensors. Yeah, so that's all. Yeah, so now coming to another application of mathematics, as I was previously mentioning, like at any point of time, how we know where our vehicle or our mobile is telling this is my current location. So mathematics is very simple. At any point of time, if you see in this picture, you are always seeing your mobile or your receiver is seeing minimum 6 to 8 satellite, 9, 10 satellites. So here you know the position of satellites are known. So if I consider x1, x2, x3, x4 are the position of the satellite along with their y and z coordinate, and unknown of your receiver is xu, yu, and zu, then you know by the very basic distance formula, this p1, p2, p3, p4 will be non-linear function of x, y, z. Now the unknowns are 4, which is one another, and the 4 I mean to the x, y, z is the position, and other is the time of your receiver. So you can find out this 4 unknown using this 4 equation. But of course, these are the nonlinear equation directly. If you go to solve by substitution method, then you may face some similarity, because here nothing but you are intersecting two sphere, and we know the intersection of two sphere is a circle. And similarly, if you have 4 such spheres, then you will get the 3 circles, and these 3 circles again will intersect and give you the point. So geometrically it is well defined, but when you are processing, you may face the similarity. So that's why this kind of equation we solve with the numerical methods, where you can apply the Gauss-Newton method or Newton-Raphson method, or many more sophisticated methods are there. But the assumption here, to know your own GPS position, the satellite position should be known. So the satellite position should be known only if you determine the position of the satellite accurately, because any error in the satellite position are going to change your own GPS positions, receiver positions. So you have to do a very precise orbit determination, which I will try to cover in 1 or 2 minutes. So as I told, the motion of the satellite is happening only due to the gravity in that, but the reality is slightly different. The motion of the satellite, the forces acting on the satellites are being disturbed not only because of the asymmetry of Earth's surface where the mass distributions are different, but also due to the atmospheric drag, the solar gravity, the solar radiation pressure, and the lunar gravity. This disturb the satellite orbit, and you now I cannot say the satellite is perfectly ellipse, but it get oscillated. So, but to have such application, you need to accurately estimate where is your orbit. So you need to consider all these forces. And if you see then now your equation of motion will become second order nonlinear differential equation, where the forces due to the asymmetry of mass distribution on Earth, which is again a Legendre polynomial, and the drag and the solar radiation pressure, all these equations will come into the differential equation, which you need to solve either through the analytical method or through the numerical methods. Earlier, people try to use the analytical method because of non-availability of good computing system. But now, since we have a very high computing system, the best method is the numerical method to compute its position in the future. So we use something like Runge-Kutta method and all to solve this second order nonlinear differential equation of motion of the satellite and solve this equation. Then you will be knowing the position and the velocity at every point of time. But here, of course, our assumption is that initial position of the satellite should be known. So I will not much dwell on this Runge-Kutta method because it's all known. Any mathematician can find out. Here the assumption is we know the Runge-Kutta method works on the first order linear differential equation. But here what we take that a, which is dv by dt, we take as a function and it becomes function of r and r dot position and velocity. So one integrator will run through that, and then once you get the r dot, then you can solve for r. But as I told, the initial condition is very, very important to solve any numerical integration. So we need to get the initial orbit of the satellite. How we do it, that is called the orbit determination. So, for example, if you have 3 stations, or if you have a satellite here over 1 station where you are getting 3 different measurement. So using these three different measurement, one can put the Taylor series and can find out what is the middle velocity of the satellite. Now, once you know the roughly what is the middle velocity of the satellite, and using this measurement, azimuth and elevation and range, one can find the position. So the position and velocity will be known using this method, which we call, you can apply the Harry-Gibbs method or some other means. So you can find out position and velocity of the satellite with some accuracy at initially itself. Then, since you have the measurement from the other stations which are tracking the satellite throughout, then you can use the estimation method of least square differential correction, and we can accurately find out what is the current orbit or current position and the velocity of the satellite at given a point of time, and that we can feed to the predictor so that we can know in the future where the satellite are going to be, and then you can plan your all the operations. And even using that only GPS satellite positions also are determined, and using that GPS satellite position you can estimate your own position. So this is how the closed loop system for orbit determination and orbit predictions went well. And another challenging problem what we have currently, because of so many launches from different agencies, like you might have heard SpaceX and all, they are launching a satellite every month more than 50, 100,000. So now currently, if you see, the situation is very tough. At every point of time, you need to maneuver your own operational satellite because many debris and other satellites are coming close to that. And the current technology is right now is only to mitigate it by just changing the orbit of your own operational satellite. But it is very challenging because in that situation you need to know the where all other objects are moving around Earth, and these are all things being solved using the very mathematical estimation theory and the prediction theory. So that's all I have from my talk. This time is very limited, and I also need to go somewhere else. Thank you all.
Thank you, sir. Are there any questions? Srinath, sir.
Thank you, Dr. P.D. Mishra. It was a quite illustrative talk, and most people might have benefited how in the space industry the applications are the maths being used. Just one small experience or your suggestion or your opinion you can tell. You being a pure mathematician, and you have turned yourself into a computational mathematics. I mean, to say a lot of computational skills are very essential for those who are doing BSc, MSc maths. Your own view or opinion, how it is important for those who are studying mathematics, this computational skills, tools, application, what is its role? Please, can you just highlight?
Yeah,
Thank
I thank you, Srinath, for asking good question, and that will also require for many young minds. So your point is right. As I did my PhD in pure mathematics, but I was always looking for the end solution. Like what we study in the academia is we try to prove some theorem, but we don't look for the applications. But what exactly happens here, or any application, you need to implement it and try to qualify through it. So my suggestion to everyone is that one thing which we are proving through our theory that this is going to happen. In my talk also I told only gravity is working on the satellite as external force is not the right things, or even I can say the satellite is moving in a circular orbit is not a correct things, because it is keep on oscillating due to the disturbances of many known forces and many unknown forces. So you need to develop your the technique with the estimation and numerical methods. Everything has to be proved, and these things are being done everywhere. You can say due to the linearization, we linearize the problem, and once you linearize the problem, then it becomes the problem of numerical methods and other things.
Okay, thank you. Any specific softwares which you suggest students, the mathematicians, to learn?
If software wise, if you go, all these things whatever I have told is really easily available in the MATLAB. If anybody is using the MATLAB, all these algorithms are well written, and if you use, you can prove yourself that how analytically I'm getting the result and how numerically it is going to be there, which can be implemented. So
Okay, thank you.
MATLAB is a good tool for doing all this.
Over to Anchor.
Venkat Raman has a question. He wants to ask, guys.
Hello, am I audible?
Yes, madam. Please go ahead.
Yeah. Thank you, sir, for your wonderful talk. I wanted to ask that alongside
Please go ahead.
alongside such these applications that you mentioned,
Yeah.
have been there have been telescopes, more more or less telescope, more of array of telescopes like the event horizon. And I wanted to ask if you can add what your experience has been onto making such imagery systems.
Yeah, of course, your question is very good with respect to the telescope. These are being used mainly for the far distance tracking and imagery system, the telescope, the optical telescope. But of course, if you see, I was telling the very baseline long interferometry system, where we need to use these things not only for the imagery system or not only to do the research about the stars, quasar and other planets, but these things are being used for our spacecraft technology also, where we try to use to navigate our own satellite using such techniques, which is one of the things the delta diver.
Just for the benefit of the audience, the person who has asked the question is an youngest space scientist, Venkat Raman. He is very enthusiastic
Great.
scientist who has attended recently many space conferences by ISRO.
Good.
Venkat, any question if you have, you can ask Dr. P.D. Mishra. He will happily answer you.
Yeah, thank you, sir. And thank you, sir, for your answer as well and for the talk. Yeah.
Thanks. Any other question? Otherwise, we'll close the session, Srinath.
I think, funny, if no questions are there, just see if we can wind it up with a thanks.
Yes, sir. Does anyone have any questions? You can raise your hand, or you can just put it in the chat box. I guess there are no questions. So let's.
You can just ask. Anybody wants to give a comment? Anybody like Dr. B.S. Shrikanta or Jayashree, Vijayashree, anybody who wish to say, you just open it up for everybody and then you can formally close it.
Yes,
Hello for everybody.
It's open for everyone.
Mishra ji and then Srinath ji. Thank you for this wonderful thing. And then I just wanted Mishra ji to just tell the student community about how important it is for them to get the very basics of math, because when they are studying, they will not be knowing how important is like parabola, hyperbola,
Yeah.
ellipse, and all those things. So ultimately, these small things will be actually a part of a big problem for like space orbital mechanics. If you can actually emphasis on these points to the student community here, so it will be benefiting them.
Thank you, ma'am. And if you see, I started after the my third, fourth slide. I just started with Newton law of gravity only, which I believe all 10th standard students they are knowing, because I also have daughter and recently taught her. So we also try to see that using so same formulas, same mathematics, we are designing our mission. Either it's low Earth orbit mission, or even it's a navigation mission, or any such missions of interplanetary also. So at their level itself, we should try to understand that when I'm just computing, okay, this is the equation of ellipse, like L by R is equal to 1 plus E cos theta, how this is going to play the role in terms of the satellite orbit, or even through that we are getting the data. So such kind of motivation only was having behind with that slide, and I hope and they will be able to connect with that. If any future anything is there, they can directly connect to me on that. Thank you.
Right. So the students here, I hope some students are there and they will be knowing that no, it is very, very important for the students to get the basics, very
Yes,
understanding of the very basics
true,
thoroughly. So that is
true.
what I just wanted to make that point through you. So
Yeah, thank you.
thank you for the wonderful. And thank you team for getting PD Mishra on board for the talk. Thank you.
Thank you, Vijayashree madam. Funny, if no questions are there, please, PD may have to go for some
Yes,
more
sir, yes,
talk.
sir.
Okay.
Okay, so there's one comment from Chandrakala in the meeting. She's saying it was good and very informative talk.
Thank you, Chandrakala.
Okay, so thank you so much for being with us, for giving us like so many insights about how mathematics is very important when it comes to physics. Like, mathematics is the language of physics, but we didn't know that like this is to an other level. Like there is no physics, it's just mathematics. Everything is mathematics.
It's vice versa, I can say.
Yeah. Okay, so thank you so much for being part of Cre'active team today, and thank you so much everyone for participating. I think we can wind up the session now. Thank you, sir.
Yeah, thank you, Srinath.
Thank
Thank
you,
you,
PD Mishra.
Suprabhya. Yeah, thank you all.
Thank
Thank
you.
you all. You can gracefully wind it up.